started by giving you a definition of complex manifold, and then we took up a number of examples. So we looked at the Euclidean space, we looked at the complex torus, which was this quotient of c to the n by a lattice. We looked at the projective space, and then we looked at this quintic, the Fermat quintic inside P4. And then I switched gears and we talked about some kind of holomorphic differential geometry. In particular, I talked about this cotangent space of the underlying real manifold. Remember, this was the notation for the underlying real manifold of my complex manifold X. And that is the usual cotangent space at the point P of this real manifold, and then I complexify it, and that complexification, which is now a complex vector space of complex dimension 2n, where n is the complex dimension of X, that has this very natural decomposition into kind of purely, what I call purely holomorphic covectors and purely anti-holomorphic covectors. It's slight abuse of terminology, but anyway, that's a useful way to think about it. Then we talked about holomorphic cotangent bundle and how these things are just, they behave very similar to what we know from differential geometry, that we have these differential elements, dz1, dz2, and these are just linear combinations of these elements, these differential elements, but the coefficients of these linear combinations are holomorphic functions which are locally defined on some open subset of X. And then we talked about the exterior algebra of this holomorphic cotangent bundle, and we saw that there's a kind of a limit to how many exterior powers you can take of it until you run out of dimensions. And the top one is what we call the canonical bundle. That's a line bundle, so its fibers are one-dimensional complex spaces. And we saw this kind of relationship that whenever, I gave it as a definition that a canonical bundle is trivial. This was the notation for trivial canonical bundle, if and only if there is a volume form on X, which was this top form with which is nowhere vanishing at holomorphic. And then we took up a bunch of examples. So we saw that on the Euclidean space, indeed there's kind of an obvious top form. You just take the wedge of all the dz's, dz1 wedge, dz2, etc. And that's a volume form. And that volume form also descended down to the quotient by any lattice because it's translation invariant, and so that showed that any complex torus also has trivial canonical bundle. And then we sort of ended with this example of the projective space. We were trying to figure out if it has a trivial canonical bundle, and in particular we looked at P1, the simplest case, and our original, simplest, most naive guess, which is just to take dz in one of the affine coordinate charts, we saw that failed. It did not define a volume form because this dz in the other coordinate chart looks like minus dw over w squared, which means, over the double intersection, of course, this is a perfectly well-defined holomorphic one form, but it does not extend as a non-vanishing holomorphic one form to the whole w chart. It obviously has a problem at w equals to 0. And there's with this one, there's just no way to fix it. I mean, these are the only two charts that we have, so there's not much we can do. And so that's very suggestive that P1 does not have a volume form, but let's try and kind of prove this more or less rigorously. So the question is, does P1, this is where we ended, does P1 have a volume form? So let's see. So suppose it does. So suppose omega is a global non-vanishing holomorphic section. So this was the notation of the canonical bundle on P1. Suppose this is true. So suppose this is a volume form. Well, then I can write it in the two coordinate charts very explicitly in terms of the coordinates and the generators dz and dw. So then, in the two trivializations, omega p1 omega p1 over the affine charts u0 and u1, we have, so in the z coordinate, it must be of this form for some non-vanishing holomorphic function, entire holomorphic function, right? I should say, entire function of z. And also, in the other coordinate chart, we have something similar. I'll call this coefficient g. So we have another. So they're both non-vanishing holomorphic entire functions. This one's a function of z, this one's a function of w. And we know that, since these are just coordinate representations for the same global one form, this function f and this function g are not entirely independent. They satisfy a relation. So where f and g satisfy or are related over the double intersection by the identity. So f of z is just change of variables. So we must have this equality, and so therefore, if I just substitute what I know of, we have this transition function w of z is 1 over z. That's the transition function. If I just use this, we have minus g of 1 over z dz over z squared. So, in other words, because this is just a generating element, it's like the coefficients in front of the same vector, it's the same non-zero vector. This equality is satisfied if and only if the coefficients are satisfied. So, i.e., maybe I'll write it like this. That the equality that f and z satisfies, that z squared f of z must equal minus g of 1 over z. That's the identity that they must satisfy. And so if I remember, these are entire holomorphic functions, so they in particular have a power series expansion in z, so I can write that. So if I do, just consider them order by order in z, I don't know what to call them, a, k, z to the k for some complex numbers ak, and similarly here we have minus power series expansion now in the powers of 1 over z. So AK and BK are some complex numbers. Now if you just stare at this, there's an inequality. If you just now compare this order by order in Z, you can see that the left-hand side, the lowest power of Z that appears on the left-hand side is Z squared. But the highest power of Z that appears on the right-hand side is 0. So if we just compare coefficients order by order, we see that the 0th coefficient here, A0, must be 0 because there is no corresponding power on the right-hand side. So A0 is 1. A1 is similarly 1. So all these coefficients must be 0. And similarly here, B0 is 0 because there is no corresponding Z to the 0 power. And B1 is 0, and so on. So what we see from this slightly rough argument is that AK, bk is equal to 0 for all k. So in other words, this is certainly not a nowhere vanishing global differential form. It is very much vanishing. It's vanishing everywhere. So omega cannot be non-vanishing. I mean, I can even say it's stronger. Omega is just 0. So what we have shown is that this entire space of global holomorphic sections over P1 of the canonical bundle of P1 is a very silly space. It's just 0. It's just the 0 vector space. It has no sections, just the 0 section. Every line bundle, every vector bundle has a 0 section, but that's it. So this is more or less a proof that P1 does not admit a volume form. And so therefore, omega P1 is non-trivial. So this is our first example of a complex manifold which has a non-trivial canonical bundle. Okay, so the next thing I want to discuss is still related to this, because in doing this calculation, in trying to compute what sections, you see what the calculation that we did here really is, basically what I did was, suppose omega is a section of this bundle, right? How does it transform? Or in other words, if I were to try and build a section of this bundle, or a bundle like it, how would I do local representations of this section in order for it to genuinely define a section? So this is a very typical technique in studying bundles. So what we have also shown is that the canonical bundle of P1 is a bundle of a very special kind. I'll give you the terminology and then we'll discuss this. So it's one of these famous bundles called OP1 of, in this case, of -2. More general, OP1 of K, an integer. So what are these guys? This is kind of a topic worthwhile knowing in its own right. The very famous useful bundles that are present on projective spaces, and this canonical bundle is one example of them. So let me give you a definition. So for any integer k, the line bundle OP1 of k, this is how you read it, OP1 of k or O of k, is the line bundle obtained by gluing trivial bundles in a very special way. Trivial line bundles over the two affine charts U0 and U1, using the transition function how do I want to write this? I'll write it like this: G01 of Z being z to the k. Or, in other words, if we want to use the homogeneous coordinates on P1, what I mean by this is z, z1 over z0. Okay. So, let me be more concrete about this. So, in other words, so very concretely, a section of one of these bundles, O of k, is nothing but a pair of functions, genuine functions, on each affine chart, which are related by a relation that is given by this gluing. That's how you should think. A section is just a bunch of functions related by a gluing, by a transition function. So it's given by a pair of functions. Maybe let me call them S0 from U0 to C, and S1 from U1 to C. So just like we had in the previous example, so in our case S0 was this representation of omega, and S1 was this representation of omega. If you like, S0 is F, and S1 is literally G. Right, anyway. So these two functions are related over the double intersection by the relation S naught of Z is Z to the K S1 of Z. S1 of, sorry, 1 over Z. You can see that this is exactly the type of identity we were writing down previously. So let's actually now, what I did here was I expanded both sides in the powers of Z, and we saw that no non-zero pair of functions can satisfy this relation. Let's see what happens in general. So imagine, these are still holomorphic functions of Z, and this one is a holomorphic function of 1 over Z. So I should be able to expand it in powers of Z. So let me do that. So here is the power series expansion of this guy. Okay, I 0 to infinity, I, zi, that's the left-hand side. And the right-hand side is Z to the K, sum from I0 to infinity of Bi Z to the minus I. And now, the observation, which we've already made in that particular example, but the observation is that if K is negative, then the right-hand side simply has no non-negative powers of Z. Right. Am I explaining this right? Yeah. So that means that if I compare coefficients, I simply get vanishing of all the coefficients, because there's no order in Z can I have an equality of something non-zero. Does that make sense? I feel like we've got all this.
There's no index overlap.
There's no index overlap. Yes, thank you. That's the neatest way of saying it. There's no index overlap if K is if K is less than 0, right? That's what I want, I think. Yeah. So what we see is that so notice if K is strictly less than 0, then AI is equal to BI is equal to 0 for all I. And so what that means Right, okay, so that's one conclusion. But another conclusion is that, now, that's for k negative. Oh, okay, this is why I confused myself, this is what I wanted to say. So now notice that, if k, if I is greater than k, so whenever I is greater than k, what this implies is that AI and BI is 0. But if I is less than k, so in particular I would need, in that case I would need k to be strictly positive. Whenever I is less than k, then I actually do have coefficients with matching powers on both sides, and so I get something non-trivial. And in particular in that case, so you see, if k is positive, then all the coefficients, like all the powers of z from 0 up to, but not including k, have to, they don't have to vanish. They are genuinely free parameters that I can modify to get degrees of freedom. So in that case, I could genuinely write down a section by just choosing those coefficients, a non-zero section, a global non-zero section. So in other words, what I'm saying is that if k is positive, then the section that I'm describing could be a polynomial of degree at most k. Yes?
It's just for the equalities that you wrote, it would be like ek minus I, right? K is equal to AI, because you still have a shift of k in the powers of z.
Yes, yeah, that's right. So, right, you're right.
Is it equivalent then, the previous example we had z squared with the positive?
Oh no, I made a mistake in my notes, and so I'm confusing out with this really basic stuff. So I think we all understand the idea, but help me make it correct. So if k is positive, right? If k is positive, then the right-hand side, the lowest power is 0, and the highest power is k, right? So
Yeah, what I said was for I smaller than k, sorry.
You were correct before.
I was correct before.
Yeah, this was 0.
Okay.
He's talking about if k is now greater than I.
I got confused, sorry.
So, is this correct?
I mean,
0.
trivially, yeah, they're all 0, so they're also equal to each other.
The second quality is if like k is bigger than I.
Like this, right?
Yeah, I think so.
Okay. God. Right, okay, got through that. Okay, so anyway, so the conclusion, this is what I really want us to understand, is that a global section of these O of k bundles, P1 of k, is a polynomial of degree k. Right, so in other words, it's this kind of thing. I0 to k, ai, zi, or in other words, again, if I want to use the homogeneous coordinates, this is z1 over z0 to the k. To that. And so, okay, so this gives kind of an important description of these O of k bundles, which, you know, worthwhile knowing. This is an important topic in complex geometry. So, if I look at the space of global sections of this bundle O of k for some k, this is, I can write it like this. So the reason I decided to write it in homogeneous coordinates is because now if I, you see, if I factor out z0 to the k, right? The rest, what I have, is a homogeneous polynomial. So that's what I'll write. So this is homogeneous polynomials of degree k in the variables z1, z0. And so, right, so now this is a kind of a genuinely rather simple vector space. You can compute its dimension. This turns out to be, well, how many homogeneous polynomials in two variables of degree k can you have? This many. That's how many coefficients you need. And the other neat observation from this, again by looking at a relation like this, is that the only one of these bundles, O of k bundles, that has a global nowhere vanishing function, nowhere vanishing section, is the one for k equals to 0. The only bundle with a nowhere vanishing section is the bundle O P1 for k equal to 0. And this is what we call the trivial bundle. Simply because as long as k is not 0, even if it's, so if it's negative, this bundle has no sections at all. If it's positive, it does have sections, but because this z with a positive power is popping up in this relation, that means...
Will have roots.
Sorry?
Will have roots.
Yeah, it have roots, that's right. It has it has a place to vanish. So the only case in which this doesn't happen is when k equals to 0, and that's the trivial bundle. Okay, so these are kind of really famous, cool bundles. And I've explained them to you over P1. They also exist over all Pn for general n. So let me just give you a definition. It's very similar. So over x, which is now Pn, for any integer k, the line bundle O Pn of k is the line bundle obtained by gluing trivial bundles over all affine charts UI using the transition map, which is again a power, using the transition map. So, for example, Gij, so that's gluing, this is over UI intersect Uj. This is just, at least the way I normalize it, Zj over Zi to the power of k. And we also have kind of a very similar conclusion. So if I look at global sections of these O of k bundles, then, you know, the reason I insisted on the word homogeneous here is because for general n, that's the only interpretation that you can have. So you want homogeneous polynomials of degree k in the variables z0, z1, and zn. And so this, if you compute this, this is C to the, what is it, K plus N, choose N. Does this make sense? Yeah.
I have a question regarding your argument to say that P1 doesn't have a nowhere vanishing bundle. So if I had a course on GR once, and then I don't know if you're familiar with it, but at some point, like we do the regular like Schwarzschild black hole in some sense, and then we see that we have a pole also in the metric.
Okay.
That pole is only generated due to a particular set of coordinates. And so it's, in the sense, it's not a physical pole in the metric, but it's a coordinate-induced pole. And so if you use another coordinate chart, then it just vanishes. So in a sense, it's only because you use a particular chart that you generate this pole. And so with your example, I'm wondering, like, you also choose two specific charts, and then you say that there's a problem also, because if you relate the two of them, then you also generate a pole. Mm-hmm. But these two charts are specific in a sense.
That's true. But now, I mean, I'll leave this to you as an exercise. So choose a different chart, right? Choose a different chart and make the same argument. Mm. And you will see that that pole persists. So it's not an artifact of choosing bad coordinates. It's something deeply intrinsic to the space. Right. Okay, so let me give you a couple of other things that is worth knowing about these O of K bundles, something that we'll use. So, they have a kind of multiplicative property which makes the notation really sing. So, important property. So, if I take two such bundles, O of K1 and O of K2, and I tensor them, I take the tensor product of these bundles, then this is a new bundle. It's still a line bundle, and it's actually an O of K bundle itself, where K is just the sum of K1 and K2.
The tensor product as a vector space, right?
Well, this is a tensor product as bundles. Now, these are bundles of vector spaces, so indeed, you can think of it as a kind of a fiber by fiber tensor product of vector spaces. Right, okay, so we've sort of, roughly speaking at least, convinced ourselves that P1 doesn't have a volume form, because the canonical bundle of P1, have I erased it already? I think I've erased it. We saw that the canonical bundle of P1 is one of these O of K bundles for K equal to -2. So let's see what happens with higher n. So a local section of omega Pn over any affine chart, let's say UI. Remember, this is the affine chart where the Zi is non-zero. And remember that I identified it with a copy of C to the n with coordinates W1 up to Wn. So this was, yeah, this. So a local section is, as we saw before, with omega of I, is really just a holomorphic function of these coordinates W. Generated by the only generator there is over this affine chart. So let's see. So, you know, if there is a volume form on Pn, if there is a volume form on Pn, then in any coordinate chart UI, it has to have this form. So in particular, you know, I can start in one coordinate chart, choose some candidate volume form, so choose some candidate holomorphic function fi, and see what it has to be, what this function has to become in other coordinate charts. So let's do this for low numbers of n. So for n equal to 2, remember that we computed the transition function was of this form. So we had new coordinates w1 tilde, w tilde, and as functions of w1, w2, this was 1 over w1, w2 over w1. And so that means that if I look at this element, dw1 tilde wedge dw tilde, I literally can just use their expressions in terms of w, in terms of w1 and w2, so that over the double intersection, u0 intersect u1, this thing is, well, let's just do the substitution. So we have dw1 is d of 1 over w1, wedge d of w2 over w1. So if you compute this, so here we just get a derivative of 1 over w1, minus times dw1 over w1 squared. And then here we have to do the product rule. So we have dw2 over w1, right? And then we have to add dw2 times d of 1 over w1. And so this gives me, so this becomes a minus, and I get dw1 over w1 squared, like this, right? But now, of course, because I'm wedging these things, right, dw1 wedge dw2 is a perfectly fine 2 covector, but dw1 wedge dw1, that vanishes because wedge is anti-symmetric, right? So I can just, this other thing that I struggled to compute, I didn't even have to. What this equals to in the end is minus dw1 wedge dw2 over w1 cubed. So, like, the thing that I want you to notice is that previously we did this calculation for n equals to 1, that's the calculation we started with, and we saw that the obvious choice for a volume form, which was dz, that one transformed to another coordinate chart gained a second order pole. Here now we cranked it up by 1, so for n equals to 2, we did the exact same thing. The obvious candidate transformed to a different coordinate chart, we get a pole of order 3. So if I do n equals to 3, what do you guess is going to be the order of the pole?
4, 5, 6.
Well, yeah. So let's do this. For n equals to 3, I won't do this in full. So for n equals to 3, the transition function between, let's say, the u0 and the u1 chart has this form, 1 over w1 W2 over W1 and W3 over W1. This was the transition function. And so if I look at dW1 tilde wedge, dW2 tilde wedge, dW3 tilde, and I just use, I just substitute these expressions, compute the derivative, what you find is that we get a power of 4 popping out. And so on. So this is what you get. So the kind of experimental observation that we get from this obviously requires a proper proof, but the observation is that the canonical bundle of p to the n is isomorphic to one of these O of k bundles, where the k is with a negative sign 1 greater than n. So it's O p1 minus k minus 1. Minus n. Minus 1. This is what we need. Does this make sense?
So just to be clear here, there is, in your definition, the Gij includes Zj in the numerator. Here it's implied because we're in that chart. Because here the transition functions are of the form Zj over Zi.
J over Zi. Oh, you mean I got this wrong?
No, it is I'm just confirming, these are the same thing because we're in the chart.
Yes. Yeah, absolutely. Yeah, sorry. I keep calling them phi, and there I call them j, but they're the same thing.
And all of these line bundles with negative integers are 0.
Say it again. All these line bundles?
With negative integers are 0.
Well, they're not 0, but they just don't have sections. Yeah, they have.
Okay.
Yeah, they have 0. They have no
Sections, that's what I meant, yeah.
Yeah, and it's because of this, the characterization that I just erased, but for p to the n, that they are the global sections are homogeneous polynomials. And of course, if you look at homogeneous polynomials of negative degree, there are none.
Yeah.
But it doesn't mean that the bundles are like 0 or trivial. They're still very interesting bundles. They just don't have global sections. In other words, another way if you can say it, if you were to magically write down a section of that bundle, you're guaranteed that that section is going to have a pole. So it's not going to be holomorphic. It's going to have some kind of problem. Which is very interesting in its own right.
The question: what is the significance of the minus in front of the one?
This one?
Yeah.
That I think has no significance.
Orientation.
Not really. I mean, these are holomorphic forms, so the orientation is not really a thing.
And is it true that it transforms with inverse fourth power if it has a minus?
Yes, because what you can conclude from this is that so S0 in this chart, if S0 is the function in this chart, S0 is 1. And S1 in this chart is minus 1. That's what you can conclude from this equality. Oh, sorry. Thank you. Right, okay, so some conclusions. So that means that OPN is non-trivial for any n, which means e to the n has no volume. Okay, let's study our last example, which is the quintic threefold, and see what happens with the canonical bundle for that complex manifold. So for x, which remember was this hypersurface, quintic hypersurface in P4. So here I'm going to give you several facts, which I'm just going to treat them as black boxes. So fact number one, which is a very famous theorem in algebraic geometry. So it's kind of worth at least hearing about it. It's called the adjunction formula. Used all the time. I use it all the time. And it says the following, at least in this context it says the following. So if I have a hypersurface inside a complex manifold, so if Y is a complex manifold and X is a smooth hypersurface, so in other words, a complex manifold of its own right, given by one equation inside Y. So just like in this example, right? We have a complex manifold, p to the fourth, and X is a smooth hypersurface in there. So if this is the case, then the adjunction formula allows you to compute the canonical bundle of X if you know the canonical bundle of Y. So the formula goes like this. So the canonical bundle of X is isomorphic to, so it's isomorphic to the canonical bundle of Y, and you need to twist it by a line bundle of a form which is very similar to these O of K bundles. So O of Y twisted by X. This is what we call it. So this is what I wrote here is a line bundle on Y, so then you just need to restrict it to X. So of course I won't explain why this formula is true. You just have to take my word for it. But it's a very famous, very, very useful fact used all the time in algebraic and complex geometry. Okay, so that's fact number one that we need. Fact number two. Fact number two explains, in our case, what these twisting line bundles are, OY of X. So if Y is the projective space and X is a hypersurface of degree d, so in other words, given by a polynomial, homogeneous polynomial of degree d, then this twisting line bundle is exactly one of these O of K bundles, where K equals to the degree of the hypersurface. Okay, so now I want to kind of apply these two facts to our situation. I'm running out of space. So in our case, so let's see, so if X in Pn is a degree d hypersurface, let's compute its canonical bundle. So let's just use these facts. So omega of X is, by using the adjunction formula, it's computed in terms of the canonical bundle of p to the n, twisted by the O of K bundle where K equals to D. And this is restricted to X. Okay. So we've computed this omega Pn bundle, and we know that it itself is one of these O of K bundles. So let's involve that. So we know that this is O Pn of minus n minus 1. And we are tensoring this with O Pn of d. Restrict this to x.
Excuse me?
Yeah.
What do we mean here by a hypersurface?
A hypersurface is just something of this form. It's a subset of p to the n in general, cut out by a polynomial. And the degree, when I say a hypersurface of degree d, it refers to the degree of that homogeneous polynomial. Right. Okay. Earlier, I also told you about this nice arithmetic property on these O of k bundles, that when I tensor them, I actually just have to add twisting degrees. And so this thing is really just O of Pn d minus n minus 1. This is restricted to x. So from this, you can see that if I'm looking for a hypersurface x inside p to the n, such that the canonical bundle of x is trivial, I better make sure that the degree of that hypersurface, d, is such that this number equals 0. So omega x is trivial if and only if d equals n plus 1. Yeah, sorry.
So what do you mean exactly by Oy of a space X?
So this you mean? Yeah. So I didn't explain it. This means it's a twisting bundle, bundle twisted by a hypersurface. One way you can interpret this, I don't know if that will make sense, is that this is the space of holomorphic functions on y which vanish along the hypersurface x. Okay. That's one way to think about it. But all we really need is just this identity, that when y is p to the n and x is a hypersurface of some degree d, then actually what these twisting guys are these O of k bundles or O of d bundles.
It's an ideal sheaf of Oy.
It's the dual of the ideal sheaf. Yeah. Yeah.
So you want to, why is that thing at the end an equivalence, and why does it not go only like as an implication? Like can't it be that you have like a bundle over Pn which is non-trivial? But
No, of course, this is not a complete argument. Yeah, I'm just giving you a flavor. Yeah, obviously.
you're saying that.
But it is equivalent. Yes. Any other questions?
Yeah, some clarification. So I get why we want it to be n plus 1, so we get the trivial bundle. But what happens if it's positive integer in the end, so bigger than n plus 1? We get this homogeneous polynomial bundle.
That's right. That's right. But remember, I also mentioned that if you look at one of these OK bundles and k is positive, then yes, you have sections.
Yeah.
But they necessarily have zeros.
Right, because they are polynomials. Yes.
Yeah. Which means no volume form. Right. Because
Right.
volume form is a holomorphic section which is nowhere vanishing. So it's a very, very strong condition. Right. Okay. So in our case, right. So in our case, in our particular example, n is equal to 4. 4 plus 1 is 5. And so that is the reason why we are studying a quintic hypersurface in P4 and not a hypersurface of any other degree. And maybe let me say one last thing about this kind of dimensional coincidence. And this has to do with string theory. So I'm not a string theorist, so I'm only going to give you a kind of inspirational flavor. So by some physical arguments, there was a realization in string theory that the universe should be made up of 10 dimensions. It should be a 10-dimensional space. This includes the 4 space-time dimensions that we're familiar with, and leaves 6 more to be discovered. For some physical reasons, these 6 dimensions need to curl up into a compact manifold. So we need a compact 6-dimensional manifold with a bunch of additional symmetries and properties, which some of them will talk about. So one of those properties is the fact that, one way to restate it is that the canonical bundle of this 6-dimensional real manifold, it has to be complex, as the canonical bundle is trivial. And so if you're looking for a 6-dimensional real or 3-dimensional complex manifold with canonical bundle, which is compact, this is exactly one of the guys that you're led to. You're led to a, you could say, okay, let's try and find such a space as a subset of the projective space. This is something that algebraic geometers like to do as a subset of the projective space. So we need it to be 3-dimensional. We need to have a trivial canonical bundle. So for it to be 3-dimensional, it has to be a hypersurface in P4, because P4 is 4-dimensional. Hypersurface means 1 dimension less. If you're looking for something 3-dimensional, that means you're looking at a hypersurface in P4. And it needs to have a canonical bundle, which is trivial. And so that really narrows it down to hypersurfaces of degree 5. And sorry? Yeah, and so that leads you to these beautiful pictures of Calabi-Yau manifolds, like the ones I showed you yesterday. Does it make sense?
Rough ideas.
Rough idea, yeah, I told you. Yeah.
Why do you expect this to live inside P4 specifically?
No, it's just an example. It's just an example. There are many other Calabi-Yau manifolds which are not of this form, but this is, hypersurfaces in P4 gives you a wealth of examples.
So the universe is compact?
Oh, well, okay.
No, we don't.
Okay. So that kind of question is a bit above my pay grade. Did you have a question as well?
Yes, but I forgot.
Okay. No?
Okay, so the conclusion here is that based on these arguments, as long as I have a quintic hypersurface and I can show that it's smooth, it's Calabi-Yau.
Well, not yet. Calabi-Yau needs more stuff.
Okay, but
it's definitely a candidate.
Okay.
To be a Calabi-Yau, yeah. I mean, we will see that it is a Calabi-Yau.
What more stuff do you need? Like Keller?
Keller.
Oh yeah.
This is what I'm about to talk about. Okay, very good. Any other questions? We should probably take a break at some point. All right. Okay, so let's restart. Let's restart. Okay, so we are now almost ready to get finally to the definition of Calabi-Yau manifold. So I just need to discuss one more topic. So we talked about what a complex manifold is. We've talked about what a canonical bundle is and what it means for it to be trivial. The final set of words that were present in the definition of the Calabi-Yau manifold that I gave you at the very beginning was this Kähler polarized business. So that's where I'm going now. So I want to explain to some extent what that means. And so for that, let me go back to this decomposition of the complexified cotangent space. So remember that we had this, I introduced this notation that for any point P, if I have a complex manifold, for any point P, we have this lambda 1P at X, and this was the complexified cotangent space. So of the real manifold underlying our complex manifold X, this was complexified. And that this thing decomposes into 2 complementary spaces, which I called LP10 of X, and lambda P10 and lambda 01 P. And what these were in local coordinates, they were just complex spans of dz1 through dzn, and the other one was a complex span of the complex conjugates dz1 bar through dz. So all.
But here we're in dimension 1, so it's just dz and dz conjugate.
dz. Why? No, it's n dimension.
Yeah, but
What's confusing?
Not one.
because here you. Sorry. No, I mean you wrote that it's the span of
Yeah.
dz1 through dzn.
Yeah.
But should it be just dz because it's the. No?
This is an n-dimensional vector space, and these are the generating
yeah,
vectors.
Right.
Right?
Sorry. I read it.
Right. So okay. So these vector spaces, lambda 1 p of x, with these decompositions, we can put them together into a vector bundle over x, which I'm now going to call lambda 1 x without the subscript p. So what this is really it's the bundle of these spaces. So for each p in x, I just take this complexified cotangent space. And so just, because every fiber has this decomposition, the bundle has the corresponding decomposition as well. So I'll write this decomposition in a suggestive way just by reusing this notation like this. So what I want to look at now is the second exterior power of this bundle. So the second wedge. So I'm going to wedge this bundle with itself. So look at second exterior power. So in other words, I'm looking at lambda 2 of x, which is, by definition, just lambda 1 of x wedge lambda 1 of x. And so what I want to do is I want to expand this in terms of this decomposition and see, because lambda 1 of x has a decomposition like this into complementary subspaces, I expect this thing to decompose in some way as well. So let's see how that works. So if I just write this decomposition like this, lambda 1, 0 of x, direct sum, lambda 0, 1, x, wedge, the same thing, lambda 1, 0, x, direct sum, lambda 0, 1, x. Now, because this is an exterior product, this is direct sum, fiber by fiber, this is just the exterior product of vector spaces and direct sums of vector spaces. We know that there's distributivity, so I can basically work with these as if they were these are kind of arithmetic operations that we're familiar with. So that means in particular that, if I expand this, then I need to wedge this guy with this, plus wedge this guy with this, and then plus this guy wedged with this, and so on. So I'm just distributing arithmetically. So what we've got is lambda 1, 0, x, wedge, lambda 1, 0, x. That's the first term. Then the second term is this wedged with this, lambda 1, 0, x, wedge, lambda 0, 1, x. And then the third term is that I need to wedge this guy with this. So I have lambda 0, 1, x, wedge lambda 1, 0, x. And then the remaining term is that I need to wedge this. Sorry, what did I do? Yeah. Mistake. So. Oh no, sorry, that's what I wanted to write. Never mind. So we wedged. Let me do this again. So I wedge this with this, and I get this term. That's the first term. Then I wedge this guy with. Then I wedge this guy with this, and I get this term. Then, if I wedge this guy with this, you see, because the wedge product is whatever anti-symmetric, what I will get is just you know, essentially negative of this wedge product, which is as vector spaces they're the same thing. So I don't have to write that extra term. So the only thing that remains is just to wedge this guy with this guy. Obviously, I'm doing this calculation in an extremely hand-wavy way, just to give you a kind of practical sense of how these calculations go. But everything I've done is mathematically solid. Just I didn't explain it mathematically. Okay, but what are these subspaces? So let me call this guy. So there's a repeated 1 in the first index, so I'll call this lambda 20x. This guy has a 1 in the first index place and a 1 in the second index place, so I'll call it lambda 11x. And then the final guy has a repeated 1 in the second index place, so I'll call it lambda 02x. So the first, so this bundle, lambda 1x, has a decomposition into two subspaces, two complementary subspaces. And once I take a second wedge power of it, I'm looking at lambda 2x, that guy has a decomposition into 3 distinct subspaces. And people refer to these as 2-0 differential forms, 1-1 differential forms, and 0-2 differential forms. Or in other words, another word that people use is purely holomorphic differential forms, mixed differential forms, and purely anti-holomorphic differential forms. And so the reason I wanted to do this calculation is that the space in the middle, this one, the 1-1, lambda 1-1 space, this is where, so Calabi-Yau geometry lives here. So that's what I want to focus on next. So now let me give you a few definitions. So definitions. So first of all, we need a Hermitian metric. So the Hermitian metric on a complex manifold X is a C infinity section of this. It's a C infinity section over all of X of the C infinity section over the real manifold underlying X of basically the tensor product of lambda 10 and lambda 01s, the ones that so the tensor power underlying this 1110. So locally, this kind of thing is given as a 2 tensor in coordinates like so, as you would expect of a metric. So I'll write it in the local coordinates on the real, on the manifold, on the real manifold underlying my complex manifolds. So I have the complex coordinates and their complex conjugates, and this gives me this total gives me 2n real coordinates. And in these coordinates, this metric is it's given by a matrix, which I'm calling Hij, matrix which which depends on the coordinates z and z bar in a C infinity way. So this is a C infinity function of these coordinates. And it's given as usual, the way you expect a metric to be. It's a 2 tensor that eats vector fields. Oops. And the important thing is that where this coefficient hij is a Hermitian metric, Hermitian matrix. Which means, what does it mean to be a Hermitian matrix? I take this matrix and take complex conjugate and transpose. That gives me the metric back, the matrix back. So whenever you have a Hermitian metric, you have there's an associated differential form. So the associated differential form called fundamental form so this is a 1-1 form. So in other words, it's a section of this bundle which I've highlighted in green. It's a C infinity section of this 1-1 bundle. And the way it's related to the Hermitian metric is very simple. You basically just take this 2 tensor and you replace the tensor product with the wedge product. So it's the 1-1 form associated with this 2 tensor. So given by, in local coordinates, again, z bar, there's some normalizing factor, I/2, doesn't matter what it is. The important thing is that it's given by the exact same formula as the Hermitian metric, but with the 2 tensor replaced by a differential 2 form. So this 2 form, this fundamental form associated with the Hermitian metric, in principle can be quite wild, but what we will require, in order to get Calabi-Yau geometry out of it, we will require that this 2 form actually satisfies a certain partial differential equation. So the fundamental form omega is called closed. We write this as d of omega equal to 0. If this coefficient matrix hij satisfies a system of PDEs, these PDEs are like this. So the derivative with respect to zk. So let me just write this. So the difference here is that k and I are being swapped places. That's the symmetry. And a similar equation so this is an equation for these are PDEs in Z, and we also have PDEs in Z bar. of the exact same form. So if you've studied differential geometry and you literally take this formula for omega that I wrote and you expand this equation, the fact that omega needs to be closed, this is what you get. This is the condition that implies this, or is equivalent to this. Yeah.
What differential do you mean with D?
This is the real de Rham differentials, the differential in Z and Z bar, not the holomorphic differential. Okay, so if I have a complex manifold which has a Hermitian metric H, such that the associated fundamental form omega is closed, in other words, it satisfies this system of PDEs, then we call such a metric Kähler. So a Kähler metric H on X is a Hermitian metric with a closed fundamental form. In which case, this fundamental form itself is often called a Kähler form. So one more word. So a Kähler complex manifold is just this data of a complex manifold X with a Hermitian metric, which is Kähler. So I'm insisting that this fundamental form associated with the metric is a closed form. That has important implications. If you've studied de Rham cohomology, you know that if you have a differential form which is closed, then it has a well-defined cohomology class. So since the Kähler form is closed, then by definition a Kähler form determines a well-defined cohomology class, which I'll denote by omega bracketed. This is the cohomology class in the second cohomology of the real manifold underlying X. And this cohomology class is often called the Kähler class. So what's the significance of having a Kähler class as opposed to an honest Kähler form? Well, if I have a representative of a Kähler class, so if I have a two form, which, or let me put it this way: if I have two forms which lie in the same cohomology class, that means they differ by something exact. So if omega, let me write it like this. If I have two Kähler forms such that their Kähler classes are equal, then I can express one in terms of the other with the correction term, which is given by something exact. So we write this as d bar of f. So for some smooth function f. Smooth global function f. Smooth in the real sense, C infinity. Sometimes called the Kähler potential. So I want to explain what this formula means more explicitly in coordinates. So concretely, if I write this Kähler form omega prime in my coordinates z, z bar, then just as before, I have a sum over these elements dzi wedge dzj bar. And so what I'm saying here is that I can express it in terms of omega. Omega, of course, was given by this matrix Hij. And what I'm saying here is that the difference between omega and omega prime is something which is what we call dd bar exact. So that means the coefficients are modified by a second derivative of some function f with respect to the two coordinates zi and z bar j. So this formula that I wrote completely explicitly in coordinates just means this. It means that if omega prime and omega lie in the same cohomology class, then they are different. There is some function f, some C infinity real valued function, global function on x, such that the coefficients of omega prime are modified from the coefficients of omega by this second derivative term of f. Okay, so the last word we need before being able to define a manifold is what I call a Kähler polarized manifold. So a Kähler polarized complex manifold is just a pair of x, and instead of giving you a Kähler metric or equivalently a Kähler form, I'm only going to give you the cohomology class of a Kähler form. So in other words, I only give you a Kähler class. Or in other words, if you want it to be even more concretely stated, then all I'm giving you is a matrix Hij, a Hermitian matrix Hij, up to the freedom of adding terms of this form. So up to choosing a smooth function f and modifying all the entries of Hij by this second derivative term. So that's the freedom I allow myself when I'm talking about a Kähler class rather than a specific Kähler form. Yeah.
Are these partial bars some differential in this lambda ijx bicomplex, or what is that?
This is all part of Dolbeault cohomology. I'm giving you very brief exposure to this, but yes, this is part of the deeper theory of Dolbeault cohomology, and these are indeed the two differentials that you have on Dolbeault cohomology. And what I'm saying is that it's this form omega in that cohomology, and so therefore, if it's closed in that cohomology, it must be any other representative of the same cohomology class must be exact with respect to the two, differential del del bar. All right, so now I finally gathered all the words that that were present in the definition of the Calabi-Yau manifold that we started with at the very beginning of this mini course. So let me just restate it now. So this is the definition that we were all aiming for. So a Calabi-Yau manifold is a compact, Kähler polarized complex manifold with trivial canonical bundle. So now that we've gone through all this hard work, we at least have some, I would say, fairly good idea of what this definition is actually trying to say. Any questions about this so far? Yeah.
So your definition in the Kähler polarization is that you use Kähler class, meaning that there is a Kähler structure. So is there some sort of intrinsic way to, like, if I just give you a cohomology class in like 1-1 to see whether it is Kähler somehow, like intrinsically, without like the need to find the Kähler form in there?
Yeah. Yeah. So what he says is correct. So you, it's not enough to just fix a closed 1-1 form, right? This is actually more or less the proof of Calabi-Yau theorem. This is how we prove it. You look for a 1-1 form which satisfies the Monge pair equation. So you need to solve the Monge pair, which is some PDE.
Right.
Which is equivalent. PDE is equivalent to looking at, so taking your 1-1 form, looking at the corresponding metric that your 1-1 form gives you, and checking that that metric is Hermitian.
Shouldn't that be somehow an algebraic condition?
I don't think so. I mean, you need that thing to be Hermitian. Sorry, maybe the other word I'm forgetting to include, it has to be positive definite. It has to be a metric. It has to be a Hermitian metric.
Still sound algebraic.
I'm not sure.
But yeah, okay, thanks.
Any other questions? Yeah.
Yeah. Maybe could you explain a bit more what is this H2 in terms of maybe what was introduced in the lecture so far?
Right. Well, this you can just say this is second de Rham cohomology. Or in other words, the space of, I'll write it like this, it's the space of closed 1-1 forms. So, like what we have with omega, right? It was a 1-1 form, and I required that it's closed up to exact 1-1 forms. What is an exact 1-1 form? So this notation means that, I can write it like this. If I only had one dimension, then this notation in coordinates, in two coordinates z and z bar, would literally be dz, this second derivative of f, dz bar times dz wedge dz bar. So this is an exact form. Exact because it's given as a second derivative with respect to z and z bar. So what we're talking about here, this is a big vector space which is given as equivalence classes. Equivalence classes of what? They're closed one forms, so things of that type, up to the freedom of adding an exact one form. So in other words, up to the freedom of adding a differential form, which is literally the second derivative of a function.
Are you viewing that as a real manifold in that sense? How does the if you view it as a real
You mean you're just confused by the fact that I wrote this? Yeah. Maybe I shouldn't. Yeah, you're right. The fact that we have all those decompositions comes from the fact that X sub R is the real manifold underlying a complex manifold. So I need that complex structure in order to use these decompositions. So yeah, perhaps you're right. I should not write the subscript R.
I was just wondering, like, so in the context of Durand cohomology,
Yeah.
what happened to, like, for example, the closed and the exact, like, two forms, for example?
Oh, I see what you're asking. You mean the fact that
Like, why are you
the usual Durand cohomology doesn't. Yeah. So this is not the usual Durand cohomology. It's the cohomology of the complex which has the D operator and the D bar operator. So it's the Dolbeault cohomology.
So it's H11, it's not H2.
Sure, it's H11, but forgetting that structure, it's in the second Durand cohomology. It's a two form. It's a real two form with a property which indeed lands it in H11. Yes.
And the confusion was the last equality there, like which says like the second Durand cohomology is the full like.
You mean this? I shouldn't write this.
Well, you'll say that there is like two 0, 0, 2 parts right inside.
Oh, that this is only included. Okay, yeah. All of these comments are valid. I certainly don't want to spend time on discussing homology. We can spend hours discussing this. But I don't want to.
Can we always find such a Keller form given? Can we always find such a Keller form given a non-empty homology group?
No. It's not particularly easy. Yeah. So finding a Keller form on a manifold is a non-trivial task. I mean, one reason is, it involves solving some PDEs. I mean, it's not trivial. It's not trivial.
You can always do it locally, though, right?
Yeah, locally you can always do it, right? Because locally you have coordinates, and the coordinates you can always write them as split like Z and Z bar, and of course we have a local candidate for a Keller form. But whether or not that thing will extend globally is a completely different matter. Any other questions?
This is a last word, I think.
Oh, you mean I shouldn't do it? Okay, so let's talk about some examples of Calabi-Yau manifolds and some examples of manifolds that are not Calabi-Yau. This is where I really want to get to. Okay, so as usual, the example number 0 is the Euclidean space. So this has the standard Hermitian metric, which is just the sum of, this comes with coordinates Z and Z bar. So you just have this very standard metric where all the HIJs are just 1. We call it H0. So this standard metric gives rise to what is called the standard Kähler form, which, again, just using all those local formulas that I wrote down, has the exact same expression, except that it's a two-form rather than a two-tensor. So because this coefficient in front of all the dzi wedge dzj, they're all 1. Those PDEs that I wrote down for closedness of omega, they are obviously satisfied because a derivative of any h would be 0. So we obviously have this, and so that means that this manifold, which is the Euclidean space, with the standard Kähler form, is Kähler. So it's a complex manifold, it's Kähler. Remember also that the canonical bundle of the Euclidean space is trivial because it has the obvious global volume form, just wedge all the dz's. So it's almost, everything, almost everything checks out for it to be a Calabi-Yau manifold, except one thing, it's not compact. So X is not a Calabi-Yau. Or maybe I should say X with the standard Kähler class is not Calabi-Yau. In this case, of course, the fault is not so much with the Kähler structure, it's the fact that X is not compact. So what about complex torus? So if I take X to be one of these complex tori, which remember was this quotient of c to the n by a lattice. So the fact that it's a quotient, again, we're going to use this to our advantage, because the standard Kähler form on c to the n, let's look at this formula, standard Kähler form on c to the m is obviously, quite clearly, invariant under translations by lambda. Remember, as we talked about yesterday, when you translate by lambda, this is like a discrete change, and so when we're doing these differentiations, this discrete change just disappears. So this omega 0 is invariant under lambda translations. So standard Kähler form omega naught on Cn is translation invariant, and so therefore it descends to a Kähler form on X. So that means that in particular, if I look at a complex torus with the Kähler class associated with this descent of a standard Kähler form, this is Kähler polarized. It's a Kähler polarized complex manifold. Recall also yesterday we discussed that the canonical bundle of X is trivial. This is because, again, for the similar reason that X is the quotient by some lattice, and the volume form on C to the n, global volume form on C to the m, is translation invariant, so it just descends to a volume form on X. And that gives you a global volume form on this complex torus. And, of course, X being a torus, a complex torus, this thing is compact. And so this is our first true example of a Calabi-Yau manifold.
Is there going to be a but?
Sorry?
Is there going to be a but?
No.
Don't you want it to be simply connected or something?
I don't. I don't care about that. But yes, indeed, I wasn't going to mention it. I think I won't mention it. So what Friedrich is referring to, let me just make it a remark. What Friedrich is referring to is that in the literature, there is, maybe to put it one way, there's a lot of disagreement about exactly what people mean by the word Calabi-Yau manifold. So I'm giving you one point of view which I think is true to the kind of classical notion, to the classical notion that Calabi and Yau themselves thought about. But there are other perspectives which some of them are more relaxed about what they mean by a Calabi-Yau manifold, and some of them are more strict. And in particular, from some points of view, from some more strict points of view, this example, some people would not consider this a Calabi-Yau manifold. Anyway, but I really don't want to get into those details. Okay, so the second example, example number 2, was the projective space. Okay, so the projective space, so this is another topic that I want to briefly explain. The projective space has a very famous metric, has a very famous Hermitian metric called the Fubini-Studi metric. Let me try to explain it to you in a few lines. But it's definitely, it's a beautiful subject it's a beautiful object to study on its own. As ever, I will try to give you a very hands-on explanation of what this metric is. So if I look at Pn and I look at homogeneous coordinates on Pn, which maybe I'll call with capital Z's. So these are my homogeneous coordinates. And now let me focus on an affine chart. So for example, over the affine chart U0, which remember is the chart where Z0 is non-zero. So I'll identify this chart with a copy of C to the n with coordinates little z1 down to zn, where zi is just the quotient of capital Zi by capital Z0. So this is the usual way we've been using these affine charts. So in this affine chart, I want to describe to you the metric that I'm interested in. So and define so H with a subscript Fs, which stands for Fubini-Studi, and it's defined like this. Actually, I want to give you the Kähler form. So the fundamental form associated with this metric, Fs. So, let me think of best way of motivating this. So if I take, if I look at this function, which is just the norm of the vector z in these coordinates, z1 to zn squared, and I look at the log of 1 plus this total length. So this gives me a real valued function on this coordinate chart, C to the n. if I differentiate it twice, once with respect to the z's and once with respect to the z bars, and then there's a normalizing factor, which I always forget, I over 2. This gives me a 1-1 form. So again, if I literally just write this out in coordinates, these are second derivatives of this function log of 1 plus the total length of the vector z. I'm differentiating this with respect to dzi and dz bar j. And this gives me a 1-1 form. So this is the definition, a very explicit definition of the Fubini-Studi metric in this chart. So then the next thing one needs to check is that if you look at if you go to a different chart, then this this expression gets glued to a similar expression in a different chart, according to the transition functions of the 1-1 cotangent bundle. So this is the Fubini-Studi Kähler form. It gives you Fubini-Studi metric, which is defined in exactly the same way. You get those. I'll call this Hij. Except now I'm looking at this as a 1-1 tensor. Oh, sorry, as a 2 tensor rather than a 2 form. And so a fact which involves calculation, not a very long calculation, but you need to do a little bit of calculation, is that this metric, defined this way, is indeed a Hermitian metric. And this 1-1 form, omega fs, is indeed closed. So this requires, as I said, it requires a computation. But what it implies is that p to the n is that this omega fs is a Kähler form indeed, and so p to the n with the associated Kähler class is a Kähler polarized manifold, complex manifold. So p to the n is a complex manifold. It has a well-defined Kähler metric, this very famous Fubini-Studi metric. It is compact. But it's not Calabi-Yau. Why? Because the canonical bundle of p to the n is not trivial. Again, I should say p to the n together with the Kähler class of the Fubini-Studi.
Sorry, here your word is.
Is not. You could, of course, it just, in a way, all I've argued here is that with this particular Kähler class, sorry, never mind. So it's, this is a Kähler polarized complex manifold, but it has a non-trivial canonical bundle. So there's no way this manifold can be Calabian. So now let me consider our final example, which is this quintic in P4. So because this is a subspace, this is a submanifold of P4, what I can do, I'll equip it with a Kähler form, omega, which is literally just the restriction of the Fubini-Studi metric from P4 down to X. Now, obviously, you know, it's not immediately obvious that that this defines for you a Kähler form, but a moment's thought, you know, what do we need of a 1-1 form to be Kähler? One thing that we need is that we need it to be closed, but that's a purely local condition. It's just some kind of local PDEs. So if the Fubini-Studi metric is closed, which it is, on all of Pn, then it's closed along a submanifold. So the closure of this 1-1 form is kind of obvious. The fact that the Hermitian metric also restricts to get a Hermitian metric, that one is perhaps slightly less easy to see, but again, a moment's thought is to, you know, you realize that it's really a kind of a point-by-point condition. So if the Fubini-Studi metric is indeed Hermitian at every point of P to the n, it's certainly Hermitian at every point of the subset of P to the n, which we call X. So I'll call H also the restriction of the Fubini-Studi metric to X. So what we get from the explanation I gave is that this pair of X and the cohomology class of this restricted Fubini-Studi metric is indeed Kähler polarized. We also know that X is compact. And earlier today, we computed the canonical bundle of X, and we saw that it was trivial. And so this, therefore, from this we can conclude that this quintic threefold in P4 is a Calabi-Yau manifold. Any questions about this?
Just to be sure, in the omega fs definition, are those all little z's now?
Yeah, they're all little, yes, sorry,
Okay,
they're all little z's, yes.
Just wanted to be sure.
Yeah. Sorry, my little z's and capital z's are sensible. Yeah, so everything on this line is little z. Yeah.
So the metric that you're putting on Pn, is it unique?
You mean this Fubini-Studi metric? That's a good question. Actually, I don't know. I don't think so. I don't think so. I think there are many other metrics that you can put on Pn. This one is somehow the most canonical, in a way that I didn't explain, but it is the most canonical.
So they would all give you the same topology quantities that you put on a metric, or?
Well, it depends on what you mean by that, but I do think that on P to the n you can put, you know, the set of Kähler classes on P to the n is non-trivial. So there are many Kähler metrics on P to the n which don't have the same Kähler class. They don't belong to the same cohomology class, which means they, you know, if you think in terms of like what would you use a metric for, or what would you use this Kähler form for, you would integrate it to get some kind of volumes, and you know. So if the two things are not cohomologous, then you shouldn't expect those numbers to agree. I mean, when you integrate.
Sure, no, this I agree, but it's just I don't know. I'm used to like regular differential geometry, and then I feel like if you have a metric, then it also, I mean, you can compute some curvature or something that will characterize the topology of your manifold. Mm-hmm. And I feel like this should be unique.
Okay, so I get, you know, another thing to say about this is that even, I'm insisting here on fixing the cohomology class of the Kähler form, not the actual Kähler form, and therefore not the actual metric. So that means I'm not actually insisting on telling you, what are the geodesics, what are the lengths of certain curves. That numbers really do depend on a particular choice of a representative of a cohomology class. And that is true even if we're choosing different representatives within the same cohomology class. So with the same Kähler polarized manifold, it doesn't yet have the notion of concrete lengths for certain curves or which curves on the manifold are geodesic. For that, you need an actual Kähler structure. Does that make sense? Sure. I mean, the geometry that you're asking for, basically you're asking about, what are the geodesics, what are the lengths of some curves. That really depends on the concrete. It doesn't depend on bracket omega fs. It depends on omega fs. Right. But things like volumes, Kähler volume. So if you integrate the Kähler form over the manifold, the Kähler volume, that only depends on the cohomology class. So these are, you could say, more intrinsic notions. More intrinsic quantities that you could associate with a manifold. Those really just depend on the Kähler class. So in some sense, this kind of intrinsic geometry, like Riemannian type geometry on this manifold X, it kind of on a, maybe let me put it this way, on a macro scale, it depends on the Kähler class, but on a micro scale, it depends on the representative. Does that sort of
somehow?
Yeah.
There is one thing that stays from Riemannian geometry. It's the volume. The overall volume is the cohomology of the, even with if you pick any representative in the cohomology class, the volume of the whole manifold is preserved.
Yes. I mean that's just the de Rham theorem.
One more question.
Yeah.
So back to the argument of restricting this to diminished 2D metric. So does it essentially work for any sub-manifold of projective space?
Yes. Yeah, absolutely.
Okay, so any sub-manifold projective space is scalar polarized by this argument?
That's right. That's correct, yeah.
If you think it's a theorem that any sub-manifold of a Kähler manifold is scalar.
Ah, okay, yeah.
That's also, exactly, yeah. That's in secret, that's what's happening here, yeah. But really, the proof of that is kind of what I said.
Everything is local, so
everything is
just check it there.
Exactly. That's the proof of that theorem. So yeah, indeed. If you take X to be any hypersurface, any hypersurface in P4, the Fubini-Studi metric will restrict to a Kähler form or a Kähler polarization, right? But that's not enough for us to call it a Calabi-Yau manifold, because the other really important thing is that it has a volume form, a holomorphic volume form. And for that, the canonical bundle needs to be trivial. And that, as we saw, there is this conflation, or there's this coincidence, numerical coincidence, that the only hypersurface that can carry a canonical bundle that is trivial in P4 is the one whose degree is equal to 5. And that 5 is 4 plus 1. That's somehow the numerics. Does that make sense? All right. Okay, so in the last, what is this, 10 or so minutes.
According to schedule, strictly speaking, you have 45 minutes left.
45?
Because it says here on the schedule it ends at 7:30.
Oh.
It's early, it's up to you.
Yeah.
Hey, man.
Somehow I So I can relax then. Brilliant. Right, okay, so the very final section, which is probably going to be the sketchiest of all the sections we've discussed so far, And I'll call it, kind of very mysteriously, I'll just call it curvature in physics. So there's going to be even fewer details here. And I just want to give you a kind of a flavor of, you know, the central ideas related to Calabi-Yau manifolds. And in particular, I want to get to the Calabi-Yau theorem and the significance. So, so first, let me say, if I have a metric on a manifold, H, what is a metric? You could say, you know, what is a metric good for? Well, a metric is supposed to be able to measure distances for you, and in particular, you know, you could ask, using metric, you could ask what is the quickest way to get from one point to another, and whether it matters if I go from one point to another using one path or another, right? So there are ranges of metrics for which the answer to this question is no, it doesn't matter if I follow one path or if I follow another path, as long as the paths can be continuously deformed one into another, then somehow the time it takes for me to get from one point to another is independent of exactly which path I take. But for some metrics, that's not the case. It really does matter whether you go over the hill or around the hill. And the thing that measures, the quantity that measures this property of dependence or independence on the path you take, the precise path you take to get from one point to another, it's called curvature. So often denoted by R of H. This is called a curvature tensor. Again, I won't get into any of the details, just to give you a very kind of brief overview of how these things fit together. And so the image when we talk about curvature, the image that you should have is roughly what I said. If I have 2 points and I want to get from one point to another, I may ask whether or not getting there using one path or using another path matters, as long as one path can be continuously deformed into another. So curvature really is the quantity that measures the discrepancy between, you could say, the time that it takes to travel from one point to another using one path. And so this is a tensor. This is a kind of a big tensor called the Riemann curvature tensor, or by other names. What people often do is, you could think of a tensor as being kind of really humongous matrix. One thing that you can do with a matrix in order to simplify it is to take a trace. So, a tensor is not just a matrix. You could say it's kind of like a multi-dimensional matrix. So when you take a trace, you get a lower dimensional matrix. I mean, those words don't really mean much, but hopefully they, jug some kind of spirit of the truth in your head. So when you take the trace of a curvature tensor, you arrive at another really important quantity, which people call the Ricci curvature. And the reason the Ricci curvature is so important, so let me just give you first a definition. So a metric H is called Ricci flat if its Ricci curvature is 0. The reason you might care about this property of metrics is that it has something to do, on a very deep level, has something to do with physics. So in physics, Ricci flat metrics are very important. So in physics, this equation, maybe let me write it like this. this equation, Ricci curvature of 0, this is nothing but the Einstein equations. Without the cosmological constant. Whatever that is.
Vacuum, empty vacuum.
Sorry?
In the vacuum.
In the vacuum, yeah. So
that's a qualifier.
So in other words, yeah, in the vacuum. So in other words, so i.e. a metric H with 0 Ricci curvature, so a Ricci flat metric, just represents vacuum solutions. Of Einstein field equations. So in other words, if somehow, you know, if you're studying physics, in particular, if you're studying string theory, right, and you by some argument or another, you realize that the 4 space-time dimensions that you're familiar with, they need to be supplemented with 6 extra dimensions, which have some symmetry properties. This whole thing it is necessarily supposed to satisfy Einstein field equations in a vacuum, because that's your space. You would be therefore looking for a manifold which has a metric, and this metric is better. This metric better be Ricci flat. So, how do Calabi-Yau manifolds come into this? They come into this through the very famous theorem. So it was first conjectured by Calabi, and then 20 years later proved by Yau. So now it's called the Calabi-Yau theorem. The theorem says the following. So suppose I have a Calabi-Yau manifold. So suppose X is given Kähler class, and this thing is Calabi-Yau. Then they say there exists a unique representative of this Kähler class, which I will call omega sub RF. Such that the associated Kähler metric H RF is Ricci flat. That's the theorem of Calabi-Yau. So if you find a Calabi-Yau manifold, so you've constructed you have constructed a Kähler metric. That Kähler metric is usually not Ricci flat. It's a Kähler metric, so it's a Hermitian metric with all the nice properties. But it's not Ricci flat. So it doesn't, as far as metric geometry, it doesn't quite describe the physical space that you're after. But what the Calabi-Yau theorem says is that this Kähler metric that you've constructed can be modified. In other words, you can change the representative that you've written down for me by some exact exact DD bar form. So in other words, you can find some function f, possibly complicated function f, to modify omega, to get a different Kähler form, to get a different metric, explicitly written in terms of omega and this modification function f, which is Ricci flat and therefore describes the correct geometry that you expect. So let me kind of finish by going through some examples again of this phenomenon. So first of all, for example 1, this was a Kähler manifold. This was the this is the complex torus. And you look at the standard Kähler metric. Which it's the standard Kähler metric on c to the n, which is invariant, translation invariant under lambda, and so it descends to x. And this one is Ricci flat. And one way to see why it's Ricci flat is, again, if you recall the formula for H naught is extremely simple. It's, all the coefficients are basically 1, and Ricci flatness is some kind of PDE, so you would expect all the coefficients just vanish when they're being differentiated. But the fact that, the reason I wanted to carry this example through is of these complex tori is precisely because of this statement. Because the fact that, I've given you a Calabi-Yau manifold with an explicit metric which happens to be Ricci flat, this is a kind of an incredible accident, just because of the simplicity of these complex manifolds. The other example of a Calabi-Yau manifold that we had was this quintic threefold, and for it, the situation is kind of completely different. So this quintic, remember that I equipped it with this Fubini-Stüri metric. And this metric is not Ricci flat. It's very far from being Ricci flat. However, the Calabi-Yau theorem, what they tell us is that in the same cohomology class as omega fs, there is a unique Kähler metric. There is a unique Kähler form whose associated Kähler metric, which I'll call HRF, which is Ricci flat, and such that omega RF and omega FS, they define the same cohomology class. So what does this mean very explicitly? I'll just end on this example. What does that mean in practice? So what this means is that there is a global smooth real value function f on the whole manifold X, such that this Ricci flat Kähler form is different from the Fubini-Studi metric simply by the derivative, by the dd bar derivative of f, by the second derivative of f. So in other words, because we know what the Fubini-Studi metric is explicitly, I give you a very explicit formula in coordinates, we can write down an explicit formula for this Ricci flat metric. And the formula is like this. I mean, I've already written the formula like this before. So it's just, we just take the coefficients, the ij coefficient of the Fubini-Studi metric, and we modify it by the second derivative of this globally defined function f. So, sorry. So, and if, you know, if that were the end of the story, then the story maybe wouldn't have been quite so interesting. The really interesting thing is that, so, you know, big difficulty, huge difficulty, lies, it's the kind of difficulty that has, you know, created many famous people's careers. The huge difficulty is that we know that such a function f exists, but we cannot compute it. So we know f exists, but it's way too complicated to describe. And so, you know, a lot of research in this field can be roughly summed up by saying that people, you know, write papers and papers on figuring out small bits and pieces about functions of this type. And this is just one example where this type of activity occurs. Simply because f happens to be a solution to some really, really complicated PDE, which is really, really difficult to solve.
So is this proof of this theorem there non-constructive?
Correct. Yeah. It's really an existence proof. Well, an existence uniqueness proof, but it's not constructive.
Do we have any quintic surface where we know f, or we are?
A good question. I don't know of any examples. I'm not an expert. Maybe there are examples where you can kind of get close to something a little bit more explicit than others. That's possible, but I haven't seen anything like that. All I know is that the kind of basically, you know, trying to get some kind of explicit handle on f is just futile. Yeah.
Are all the assumptions in the Calabi-Yau theorem like necessary? So you can't find the Ricci flat metric on the projective space, for example?
That's correct, yeah. So the answer is yes. And so, for instance, the reason you can't find the Ricci flat metric on Pn obviously has to do with the fact that the canonical bundle of Pn is not trivial. So that means the volume form doesn't exist. And so that is essentially the way you construct this f, or the way you show that this f exists, is you need to study a certain equation which is basically equivalent to a type of Monge-Ampere equation. And so if you don't have a volume form, then that Monge-Ampere equation is somehow ill-defined. And that's roughly what's happening.
Same argument for compactness. Oh, sorry. Same argument for compactness.
Sorry?
For compactness is the same thing.
Yeah, it's something. It must be something like that. I'm not quite sure. Yeah. Sorry, your question was?
Yeah, at least were we able to approximate f?
Yeah, that's certainly one. You know, one.
So type of not interpolation. Interpolation is more basic, but something like it.
Yeah, I mean that's one way that people study this. Yeah,
because if you can't attack it directly, like
well,
approximate.
You know, there's lots of methods that people apply. Some kind of approximation. Approximation techniques. So when I say approximation, I really mean, you know, you try to kind of expand it in some kind of parameters, etc. And that is you know, one way you can access certain properties with this function. But still, it's you know, you get only very partial information. But I wouldn't say you can like numerically. That's, I mean, probably some people try and do that, but I'm not quite sure what the state of that would be. Any other questions? So I'm leaving you on this, in some ways, very satisfying that, you know, there's still so much that we don't know, and in some ways very unsatisfying that we've worked so hard to get all this machinery going, only to find out that in order to actually write this thing down, you know, it's better not to. But I hope this was interesting. Okay, anyway, thank you very much.